Hi, I'm Andrew Steeren, and this is Faithful Heteroscedastic Regression with Neural Networks. Homoscedastic regression assumes that the conditional mean of response variable y is the output of some unknown mean function f operating on the covariates. Its other assumption is that covariance is global, which is often a convenient rather than accurate modeling assumption. Heteroscedastic regression establishes that covariance is also the output of some unknown function g operating on the covariates. Thus, the goal of heteroscedastic regression is to find functions mu and sigma to approximate f and g. The idea to use neural networks for these approximating functions goes back 3 decades, and to do so, one minimizes the negative log likelihood using standard backpropagation of gradients. Unfortunately, this conventional fitting procedure can result in heteroscedastic models with poor predictive performance. Looking at the negative log likelihoods gradients with respect to the model parameters estimates explains why. Mean estimates for points with no nearby covariates can destabilize learning. As mean errors go to 0, so too does variance, which can produce inappropriate large updates from minuscule errors. Furthermore, mean fitting is biased towards regions of data with low measurement noise. And perhaps the most deleterious outcome is when a model uses high variance to explain a poor mean estimate during optimization. This downweights that point's learning signal, creating a rich-get-richer dynamic where points with poor mean estimates are continually ignored despite the mean network being flexible enough to improve estimation at these points. This figure demonstrates this last problem. On the left, we plot the mean and the variance output of a homoscedastic model with unit variance during optimization. The mean converges to the true mean function both on the data-rich interval between 2.5 and 7.5, as well as on the two road points at 0.5 and 9.5. Regions with data have gray backgrounds for visual convenience. In contrast, the heteroscedastic model, after fitting its mean function to the data-rich interval, has a drastic error at 9.5, which uses high variance to explain. Doing so depletes this point's learning signal so significantly that it is not able to recover. A neural network that parameterizes a heteroscedastic regression model has 3 components. Representation learner ftrunc maps covariates onto some representation z that then feeds mean and covariance output heads. Ftrunc can be the identity function in the case of separate mean and covariance networks, or any number of hidden layers. Similarly, the mean and covariance parameter heads can have single output layers or be deep networks themselves. This partitioning allows us to deconstruct the full heteroscedastic model G into its homoscedastic mean-only network Fmu by removing all computations that are not ancestors of the mean estimate. This subnetwork's parameter space is a subset of the full networks, and more critically, however, is the observation that G and Fmu are equally as powerful at mean estimation. Therefore, we propose baselining the mean performance of G to the mean performance of Fmu. If, after separately optimizing the mean-only model and the full heteroscedastic model, the mean square error performance of the heteroscedastic model is as good or better than its mean-only baselines, then we say it is faithful. We can provably ensure faithfulness by making 2 small changes shown in orange. First, we scale the gradient with respect to mean estimates by its inverse Jacobian, the covariance. This can be interpreted as a Newton step, or as the gradient of a homoscedastic model with unit diagonal covariance. Second, we block the covariance gradients from influencing the representation learner's parameters. And these 2 changes ensure that G is provably faithful to Fmu. Implementing these changes in any deep learning framework is incredibly straightforward. Using our alternative loss function, which minimizes the sum of square errors of the mean estimate and the negative log likelihood of the covariance output head. The floor operation denotes the stop gradient operation, which treats its operands as constants. Differentiating this loss, one finds that the shared representation learner and mean output head have gradients equivalent to minimizing the sum of squared errors of a homoscedastic model, thereby ensuring their faithfulness. To avoid confounding model performance and model selection, we group methods according to the predictive distributions form. First, we have normal predictive distributions, which include conventional negative log likelihood minimization, as well as the recent beta NLL loss. Second, we have Monte Carlo dropout methods, where the predictive distribution is a mixture of normals under different dropout conditions. Third, we have deep ensembles, which is also a mixture of normals, but arises from an ensemble of models that experience different randomness during optimization. Lastly, we adapt our proposal to the student's t distribution and compare the methods with student's t predictive distributions. Please see our appendix for details regarding our adaptation to this distribution. For our normal predictive models, we utilize the same toy data where the conventional negative log likelihood minimization fails to converge on isolated points. Here, we find the beta NLL with beta set to 0.5 has not achieved convergence at 9.5 in 20,000 epochs. The beta NLL with beta set to 1.0 and our method converge on both rogue points and well approximate the true mean and variance on the data-rich interval. We then examine performance on various UCI regression datasets. On the left, we have the RMSE, expected calibration error, and log likelihood for a unit variance homoscedastic model. To the right, we consider heteroscedastic methods with normal predictive distributions. We strike out all values for any performance where the model's RMSE is worse than the homoscedastic model's RMSE according to a one-sided paired t-test. As one can see, conventional NLL minimization is frequently unfaithful. The beta NLL is unfaithful a handful of times as well. Our method is never unfaithful and has the best expected calibration error and log likelihood with respect to all faithful performances. We find these results hold for Monte Carlo dropout. Conventional heteroscedastic Monte Carlo dropout fails to converge on x equals 9.5, whereas ours does. Additionally, we find massive performance gains for the UCI datasets. This holds again for deep ensembles, and once again for student fees-based methods. We expect our model's variance estimate to capture two types of uncertainty. Epistemic uncertainty is that which can be reduced by collecting more data or by refining your model. In the Bayesian world, this can be thought of as model parameter uncertainty. Aleatoric uncertainty is that which cannot be so reduced. So an example of that would be measurement noise or noise variance. We now examine if we can learn the true underlying noise variance from our well-calibrated model. Beginning at the bias variance inequality, we rearrange terms to find that aleatoric noise variance is the difference in our estimator's mean square error with respect to noisy response variable and their mean, respectively. A well-calibrated model will approximate these terms when trained separately on noisy and denoise data. We use VAEs in the MNIST dataset as a proof of concept. We argue that training a heteroscedastic VAE to reconstruct digits should only capture epistemic uncertainty of the mean and its variance estimates. On the left, we have clean data. The homoscedastic VAE has good-looking means, so we know our architecture is sufficiently flexible to achieve good reconstructions. The conventional VAE falls into the rich get richer cycle of explaining poor mean estimates with high variance. The beta NLL and our method have good-looking mean estimates, and their variance estimates suggest the VAE mean estimates are most uncertain at edge localization. On the right, we corrupt data with heteroscedastic noise that depends on the digit's true but unobserved label. The homoscedastic and conventional VAEs behave as before. The beta NLL and our method retain the good-looking means, but we now see a rectangular patch in addition to the epistemic edge localization uncertainty. Indeed, this patch is the noise we added to the images. We rotated additive white noise according to class label. Averaging the difference in variance estimates between noisy and clean data conditioned on class label, we find that the beta NLL and our method recover the true heteroscedasticity in the data. Having validated our method, we then considered the real-world problem of studying sequence-dependent heteroscedasticity in CRISPR-Cas13, an RNA targeting gene knockdown system. My collaborators collected 3 Cas13 efficacy datasets that vary in cell type and measurement technology. For each of these datasets, we have 2 to 3 measurements per target sequence. We trained our model on the raw replicates and then again on their average. The average SHAP values for the mean estimates appear in the first 2 rows. Negative values indicate a more effective sequence. The next 2 rows are the average SHAP values for the variance estimates. We see the expected reduction in magnitude when the model is trained on the denoise measurements. Taking their difference allows us to visualize noise variance's dependence on sequence. This analysis is a first of its kind for CRISPR-Cas13. Thank you for listening.